So today we're going to be covering a few concepts that you may not have come across before. The first one is stress, and it's denoted by this sigma, which is a Greek letter, and this is given by the force over the area exerted on a particular material. So let's say you had this material of thickness d, and some force of, let's say, T was applied to it for tension. Well, then the force over the area, well, the area is pi d squared over 4. This is because the area of a circle is pi r squared, and r is equal to d over 2, so that's equal to pi d squared over 4. So your sigma value or your stress value is going to be T over pi d squared over 4. That's just an example for a circular cross section. The unit for force is in newtons, and the unit for area is in meters squared. So the unit for stress is newtons per meter squared, or you can give it in pascals. And another concept is strain, and this is denoted by the extension of a material over its original length. So let's say the strain is denoted by this epsilon here. This is equal to x over L. So let's say you had this string or wire of original length L0, and you extend it such that its new length is L1. Well, the extension is equal to L1 minus L0, and your strain value is going to be equal to x over L, where x is your extension, so L1 minus L0, and capital L is your original length, which is L0. So that would be your strain. Now, the strain is just a ratio between extension and length. So the extension is given in meters, and the length is also given in meters, so the strain has no units. Now, there's a property called Young's modulus, and this is something that is unique to each material. It's like a density or a resistivity. Every different type of material has a specific Young's modulus value. So for gold it might be something, for steel it might be something, for rubber it might be something. And the Young's modulus, which is given by this E, is equal to the stress of an object over its strain. We know that stress here is F over A, and that strain is X over L. So if we do some rearranging here, we can get that the Young's modulus is equal to FL over AX. Now let's look at some units. The units for Young's modulus is in newtons per meter squared, or you could say that is in pascals. So now let's analyze some properties of a stress versus strain graph. Well, we know that the Young's modulus is equal to stress over strain. So if you plotted a graph of stress versus strain, you'd get a straight line through the origin, and your gradient here would be equal to your Young's modulus. That's because if you were to rearrange this, you'd get sigma is equal to E times epsilon. This is your Y value, this is your X value, so your gradient is Young's modulus. Now, if I plotted a force versus extension graph, well, if you remember from the equation before, we said that the Young's modulus is equal to FL over AX. So if I rearrange this to make F the subject, you'd get F is equal to EA over L times by X. F is your Y value, the extension is your X value. So then your gradient would be this quantity here. And this again would therefore be a straight line, where the gradient is equal to your Young's modulus times your area over the original length. So from a practical standpoint, how can you determine Young's modulus for a spring or something like that? Well, what you'd actually do is you'd do the same setup as your Hooke's law experiment, where you had your string and you're varying the load added onto that string, and you're measuring the extension for each mass you add. If you're unfamiliar with this experiment, watch the Hooke's law video. But to this experiment, we're going to add two more measurements. What you're going to do is you're also going to measure the cross-sectional area of your wire or your string, whatever it is. And if it's of a circular cross section, you can measure the diameter using a micrometer. Remember, you do this at 3 different points along the string, and then you take a mean. So you'd get three different diameter values, and your area in this case would be pi d squared over 4. And you'd also measure the original length using a ruler. So as in the Hooke's law experiment, you'd get a force versus extension graph. And we have just found out that for a force versus extension graph, the gradient is equal to the Young's modulus times the cross-sectional area over the length. So if you were able to work out the gradient of this graph, the Young's modulus will be equal to the gradient times by the original length over the cross-sectional area. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.